Hello, welcome to the video. In this video, we're going to learn about the energies of bonds and solids and how the strength of one bond can be used to calculate the stability of 1 mole of a crystalline solid. We'll start with individual bonds between two atoms and models for the bond potential. We'll see that these models vary with the type of bonding. We then examine how to use the energy of the individual bond to calculate the cohesive energy of a mole of crystalline solid. Now, a mole of solid contains many bonds, and it's important that the number of bonds are counted correctly. We must also consider if it's reasonable, at least to a first approximation, to assume the bonds in the solid are restricted to the nearest neighbor atoms, or if longer-range interactions that extend well beyond the nearest neighbors must be taken into account. For ionic solids, we'll see that the longer-range interactions cannot be ignored, and we'll discuss the so-called Madelung constant and use that to calculate the cohesive energy of the ionic solid. Finally, we look at the best way to make quantitative comparisons between the strength of the bonding in different solids to correlate their bonding to their physical properties, for example, their melting points. I hope you enjoy it. We'll begin by looking at the bonding energetics of a single bond in a solid. As the two atoms approach each other, the attractive forces lower the energy of the system to provide a bonding interaction, and the energy is negative compared to the separated atoms. Let's bring these two atoms closer together and we can follow the change in the energy with distance. So as they approach, the energy is lowered. However, we reach a certain point where the distance is too short, and repulsive forces due to electron cloud repulsions, which are very short range, raise the energy compared to the separated atoms. And so we have a balance between these attractive forces and the repulsive forces at the shorter distance. Let's plot these two different energies as a function of the separation. First, the attractive energy. These are the bonding forces providing a driving force for the atoms to attract each other. And then at that shorter distance, we have a repulsive energy which rapidly increases at the shorter distance. And then the overall or net energy, the overall bond potential shown in red, is the addition of the two. The minimum energy, E0, is the equilibrium bond energy, and that occurs at the equilibrium bond length, R0. At the equilibrium distance and the lowest energy, the forces exerted by the repulsive and attractive interactions are balanced, and this is the equilibrium bond length of the system. The magnitude of the bond energy, E0, is very much dependent on the nature of the interatomic forces in the system. And as I'm sure we're familiar with, the stronger bond types, ionic, covalent, and metallic, yield a more negative E0. Weaker forces such as van der Waals, or hydrogen bonding, or weak dipole-dipole interactions, E0 is much smaller. And we see here in this table, there's essentially a scaling between the melting point and the magnitude of that bond energy. We should note here there's a considerable range of forces within any given type of bonding. For example, ionic, we can see large variations in these energies. Even though they're large, they can still vary by a considerable amount, yielding a variation in melting points. Another good example are the metallic forces and the elemental metals. We may think they're strong for all systems, and indeed for some they are, such as tungsten, where that bond energy, minus 850 kilojoules, is very large and yields a very large melting point, over 3000 degrees. However, we know another metal, such as mercury, is a liquid at room temperature, and the forces are much smaller, so there's a considerable range. We'll return to the scaling between melting point and bond energy a little bit later. Let's look now at different models for the bond potential. So the net energy is the sum of the attractive energy and the repulsive energy, where again that attractive energy is negative, and here the repulsive energy is positive, and typically it's in dependence on 1 over r. In van der Waals solids, where the atoms are not charged, they are neutral, this exponent here for the attractive forces is typically 6, and for the repulsive force it's much larger, in this case 12. This larger exponent for the repulsive force is consistent with their short-range nature, and so while they are very large at very, very short distances, they drop off rapidly with r. A widely used model for this potential curve is the so-called Leonard-Jones pair potential, shown by this equation, where again we see the repulsive term has this exponent to the 12, and for the attractive term the exponent is 6. At the equilibrium distance, the bond energy from this potential is equal to epsilon. For example, in neon, this energy is very, very small, 3.1 times 10 to the minus 3 eV per bond. This model for the potential works very well for simple van der Waals systems. But for other neutral atom systems, such as in metals or covalent solids, it does not work that well and must be modified. And indeed, some of the modifications are quite complicated, requiring extensive computational calculations. Turning now to ionic systems, let us take a look at simple models for the bond potential of an ionic bond. So here's our picture of an isolated ion pair. Our equilibrium bond distance is r0, and that is actually the sum of the radius of the cation and the anion, which touch at that equilibrium distance. The general equation for the bond potential is shown here. The attractive term now is 1 over r to the power 1, so n is 1. That repulsive term still has a high value for the exponent. Usually it's in the range of 8, again indicating that these electron-electron repulsions at short distances drop off quite rapidly. A here originates from the electrostatic potential derived from the attraction of the oppositely charged ions. For an isolated cation-anion pair, this equation rearranges to the following, where Z plus, Z minus are the absolute formal charges on the cation and anion respectively. R0 is the equilibrium bond length. E is the elementary charge, shown here in coulombs. Epsilon is the permittivity of free space, and this 1 over 8 again is derived from those repulsive terms, those electron cloud repulsions at very short distances. So this equation allows calculation of the energy of the cation-anion pair from simple electrostatics and is called the Born-Lande equation. Well, given that we have equations for an individual bond in the solid, how do we calculate the molar crystal energy from the energy of a bond pair? So in a bond pair, each atom just has one nearest neighbor. It's isolated. But in a solid, we have many, many atoms with many, many nearest neighbors. And so the issue is, how do we account for the nearest neighbors increasing to yield the molar crystal energy? Well, if we only consider nearest neighbor interactions, and that can be a big if and a fairly large assumption for some systems, but if we go along with that assumption, the energy of the crystal is just the sum of the energy of all the nearest neighbor bonds. The number of nearest neighbor bonds per atom is the coordination number of the crystal structure. And so now, for 1 mole of atoms, the total number of nearest neighbor bonds is Avogadro's number, multiplied by the coordination number of each atom. That tells us the total number of nearest neighbor bonds, but we must divide that by 2 to avoid double counting of bonds for the different atoms. So now we can get a fairly simple equation for the molar energy of a solid, where this first term is the energy of a single bond multiplied by the total number of nearest neighbor bonds in 1 mole, and the last two terms are just converting units from eV to kilojoules. So in essence, if we just consider nearest neighbor interactions, then by counting appropriately the number of nearest neighbor bonds in 1 mole of the solid, and multiplying that by the energy of the isolated pair, we should then be able to convert the energy of a single bond to the energy of all of the bonds in 1 mole of a solid. Let's look at some examples using this equation. Let us look at a van der Waals solid, for example neon. The energy of a single bond pair, a neon-neon bond, it's very small, it's minus 3.1 times 10 to the minus eV per bond. Neon solid forms a face-centered cubic, close-packed structure in which the coordination number of the neon atoms is 12. Just plugging this into this equation up here, then we will find the molar energy of neon is minus 1.8 kilojoules per mole. We can also apply this equation for converting from single bond to molar energies for extended covalent solids. For example, let us look at diamond. The energy of an isolated bond is minus 3.7 eV. The coordination of carbon in diamond is 4. Plugging these numbers into this equation, which of course counts for the double counting of the bonds, then we'll find the molar energy is minus 713 kilojoules per mole. Diamond is a very stable, strongly bonded system. Let's take a look at metals. For example, tungsten. The energy of a tungsten-tungsten isolated bond is 2.2 eV per bond. Tungsten has a body-centered cubic structure with a coordination number of 8. And so therefore we can calculate the molar energy, and in this case it's minus 850 kilojoules per mole. Again, tungsten is a very strongly bonded solid, and it has a very high melting point. But let us note, in all of these examples, we've made one major assumption. We're ignoring any atom-atom interactions beyond the nearest neighbors. In fact, for extended covalent solids and metals, that assumption starts to break down. But the assumption is totally impossible for ionic systems. We now turn to ionic systems. Before, we've seen that the energy of an ionic pair can be calculated from the Born-Landau equation shown here. However, electrostatic interactions extend far beyond nearest neighbors, and so when the ion pair is inserted into the crystal, we can no longer limit our considerations of the molar energy to the nearest neighbors alone. And so in the crystal, the electrostatic interactions are not just between a cation and its surrounding anions. We must also consider longer range interactions. Let us look at the rock salt structure as an example, with the equilibrium bond distance of one bond being R0. Let's pick a given site, for example the sodium cation site, and look at the electrostatic interactions. Well, first of all, we're going to have that nearest neighbor interaction, shown here. And we have an attractive interaction between sodium and chlorine. And in the crystal, because the coordination number of the sodium cation is 6, there are 6 nearest neighbor chlorine anions at a distance R0, and that interaction is attractive. That is our nearest neighbor interaction. However, a little bit further away are other sodium cations, shown in green. So at this distance, which from the geometry is R0 times root 2, there are in fact 12 sodium cation next nearest neighbors. And those interactions will be repulsive. So at this stage we have 6 attractive at R0, and then 12 repulsive at R0 times root 2. Well, we go out a little further to R0 times root 3, and we'll find now there are 8 next nearest neighbor chlorine anions, and those 8 will have attractive interactions with that sodium cation. As we keep going further away, we will discover more interactions. So at a distance 2r, we'll find 6 more sodium cations, and those interactions will be repulsive. And then at r root 5, there are 24 more chlorine anions, also giving attractive forces. And we can keep on going. And when we sum these interactions, we can gain insight into total overall electrostatic interactions within the crystal. So shown here is that sum, the first term, negative, attractive, between our sodium and 6 chlorines. Here's our 12 next nearest neighbor sodiums, repulsive interactions, R0 times root 2, etc. And this sum is 1.748 for the sodium chloride crystal. And this is simply a geometric factor, and we call this M, the Madelung constant. It sums the overall electrostatic interactions in the crystal for the ionic pair, or as we should call it, the ionic formula unit. In this case, the NaCl formula unit. It's a geometric factor, and the value solely depends on the type of structure and therefore the coordination numbers of the cations and the anions. And as we just mentioned, for sodium chloride, this sum is 1.748. Now let's look at the molar lattice energy of an ionic solid. We already have our formula for calculating the energy of an isolated formula unit. To calculate the energy of this formula unit in the crystal, we multiply it by m, the Madelung constant. And so this is a little different to the neutral atom systems. For those neutral atom systems, we took the energy of the isolated formula unit and multiplied it by their nearest neighbor coordination number and divided that by 2 so we didn't double count bonds to get the molar energy. Here we don't, because we have to consider longer range interactions. And so we take the geometric sum of those and multiply that by the energy of that formula unit. And so now for 1 mole we have Avogadro's number of formula units. And so the molar energy is the energy of 1 formula unit in the crystal. We have Avogadro's number of formula units. That will give us then the molar energy in eV. And these last 2 terms are just to convert from electron volts to kilojoules. And so at the bottom is our final equation for the molar lattice energy of an ionic solid. The energy of 1 bond multiplied by our Madelung constant multiplied by a conversion factor that adjusts my units to kilojoules per mole. Shown here are the values of the Madelung constants for different types of ionic solids. So as we just mentioned, the Madelung constant is a geometric factor summing the electrostatic interactions in the crystal, and by definition it must change with the coordination number of the cation and the anion in the structure. So let's first look at some AX solids. If I had an isolated ion pair, the coordination number of the cation and the anion are both 1. And actually the Madelung constant for this arrangement would be 1. For the zinc blend structure, where the coordination number of both ions is 4, the Madelung constant 1.64, and then it steadily increases from zinc blend to rock salt, coordination number 6, to the cesium chloride structure, where they're both 8, and the constant is 1.763. And so increasing stabilization as I increase the coordination number. We can see the same trend in AX2 type ionic solids, going from, in this case, quartz to rutile to fluorite, where the coordination number of the cation is increasing from 4 to 6 to 8, and that of the anion from 2 to 3 to 4, and correspondingly the Madelung constant also increases. What I show here in parentheses is the value of the Madelung constant per 2 ions. In other words, here in the AX2 structure, there's a total of 3 ions in the formula unit. And so it's sort of an unfair comparison, if you like, to compare the electrostatic interactions here to an AX because there's more ions in the AX2 unit. And so to make that comparison, we take the value of the Madelung constant for an AX2 structure and just convert it to a 2-ion basis. And finally, here is an example of a Madelung constant for the alumina structure, A2X3. Alumina has the coordination numbers of 6 and 4, respectively, for the cation and anion. Madelung constant is 4, but if we convert it to a 2-ion basis, it's 1.6. And so then if we compare all of these Madelung constants for the 2-ion basis, we'll see a steady increase with the coordination number. The bottom line, the Madelung constant is structure dependent and it increases with coordination number. Now let's turn to calculating the molar lattice energy of some ionic solids using our previously derived equation. Plugging in the various constants, the charge, the electronic charge, the fundamental charge in coulombs, and the permittivity of the vacuum of free space, and our so-called Born exponent, our repulsion term, which is 8. Then for the sodium chloride structure, the rock salt structure, sodium chloride is just one example of a compound having this geometric arrangement. The Madelung constant is 1.748. We can look up the ionic radii of sodium and chlorine to get the equilibrium bond distance, which is as shown. Plugging in, we calculate the molar lattice energy of sodium chloride is about minus 750 kilojoules per mole. Now if we go to alumina, or the corundum structure, an example is alumina, Al2O3. Here the coordination numbers of aluminum and oxygen are 6 and 4 respectively, and the Madelung constant is quite high, 4.04. Partly because, of course, we know there are more ions in the formula unit. The bond distance from the radii of aluminum 3 plus and oxygen 2 minus is 1.915, and we'll calculate a molar lattice energy, which is huge, minus 15,000 kilojoules per mole. This is a result of two things. Number one, the higher Madelung constant. Number two, the higher charges on aluminum and oxygen. The product of the two charges for sodium chloride was just 1. Of course, for Al2O3, it's 6. And finally, it's larger because there are just simply larger number of ions in 1 mole. Because our formula unit contains 5 ions compared to the 2 in sodium chloride. What is the best quantitative measure of the strength of the bonding in a solid? We've mentioned a few. Is it the molar cohesive energy? Is it the strength of one bond? Is it the cumulative energy of all of the bonds that are formed to a given atom? What is the best measure that we should use? Well, molar energies are certainly one measure. Yes, they depend on the energy of a bond, and yes, they depend on how many bonds a given atom forms. However, they also depend on the number of atoms in the formula unit, as I've mentioned before. So, for example, if the molar energy of a compound AX was minus 1,000, and the molar energy of a compound A3X5 was minus 2,000, is it correct to deduce that A3X5 is more strongly bonded because it has the more negative molar energy? Well, no, not in this case, because A3X5 contains 8 total atoms, AX only 2, and so because A3X5 contains 4 times as many atoms, then for A3X5 to be the more strongly bonded material, it would have to have a lattice energy that was at least 4 times greater than AX. And in my example here, it does not. In fact, the most widely used measure is the bonding energy per atom, per ion, and per molecule. Let us take a look at that and see how it is calculated. Again, we're going to have to be careful and distinguish between non-ionic solids and ionic solids. So for non-ionic solids, the bonding energy per atom, or if it's a molecular material, per molecule, is the energy of one bond to that atom multiplied by the number of bonds it forms. So in terms of an equation, I would have the energy of one bond. Well, one bond comprises 2 atoms, 2 nearest neighbors, if you like, So I should divide that by 2 if I want to ascribe a certain energy to each atom that's participating in that bond. So far I have the energy, in orange, of 1 bond per atom. And then I multiply that by the number of nearest neighbors that that atom has in that particular structure, the coordination number. And that would give me the total bonding energy per atom in the structure. As an example, let's look at diamond. The energy of 1 bond in diamond is 3.7 eV. And so the bonding energy per carbon is 3.7 eV divided by 2, because there's 2 atoms in the bond, then multiplied by 4, because that is the coordination number of each atom. And so the bonding energy in diamond per carbon is 7.4 eV per atom. Let's look at another example, a van der Waals bonded example. Again, let's go back to neon, which is face-centered cubic. The energy of a bond in neon is quite weak, 3.1 times 10 to the minus 3 eV. And now if we want to ascertain the total bonding energy per neon, I take the energy of the bond, recognize there's 2 atoms in it, so half the energy of the bond is due to each atom, multiplied then by the number of bonds each atom makes, which is 12. So the total bonding energy per neon is 0.019 eV per atom. Finally, let's look at another example, a metallic example for tungsten. Tungsten is body-centered cubic. The energy of a tungsten-tungsten bond is 2.2 eV. That means each atom in that bond is giving it 1.1 eV. Multiplied then by the coordination number, body-centered cubic, coordination number is 8. Each tungsten forms 8 bonds. And so the total bond energy per tungsten is 8.8 eV per tungsten. Now for ionic systems, again we've got to be a little bit careful. The bonding energy per ion is the energy of a formula unit in the crystal divided by the number of ions in that formula unit, as shown in this equation. Let's use an example. The energy of a bond within the sodium chloride crystal, in other words, we have already corrected using the Madelung constant to get that energy, is 7.7 eV per unit, per sodium chloride unit. There are 2 ions in that unit, and so the energy per ion is this number divided by 2, minus 3.9 eV per ion. We don't have to start counting all of the bonds around each ion, as we did for the neutral systems, because that's already been factored in calculating the energy of each unit in the crystal through the Madelung constant. So this number has already corrected for the coordination number issues. Also alumina, we know the energy per Al2O3 unit in the alumina structure is minus 159 eV per unit. Again, that's already corrected through the Madelung constant for the various coordination numbers and all of the electrostatic interactions. There are 5 ions per formula unit, and so the bonding energy per ion in alumina is minus 32 eV. Now let's go back to bond strength and melting points, where we're trying to make a direct connection between melting point and the strength of the bonding of the species in a given crystal. The best representation is the bonding energy per atom, ion or molecule, whatever the constituent units are in the substance. And we'll see here for each bond type there is an excellent correlation between the strength of that bonding per ion, per atom or per molecule and the resultant melting point.